Okay, 3,000 feet, and then you have a launching pad. Okay, and then rockets going up. That's my rocket ship. Okay, if the rocket is rising vertically at 880 feet per second, so if we call this y, that means they're giving me dy dt. It's going to be 880 feet per second. When it is 4,000 feet above the launch pad, so that says when, okay, y is equal to 4,000 feet. Okay. How fast must the camera elevation angle change at the instant to keep the camera aimed at the rocket? So this is my camera elevation angle right there. Okay, I'll call that theta. So they want me to find change in the angle with respect to time. Okay, alright. So right now it deals with this angle, this opposite side, and the adjacent side. So that means we're going to use tangent of theta is equal to opposite over adjacent. That's my model that I'm going to use, and of course I'm going to multiply both sides by 3,000, so it will look like this. You don't have to, but I like to do it that way. Now I'm going to take the derivative of this. Before I take the derivative of this, check and see you have all the information. When I take the derivative here, I'm going to get d theta dt, and I'm okay because I'm trying to find that. When I take the derivative of this, I'm going to get dy dt, and I'm okay. Okay, so that means I don't need to do anything before we start. Let's go ahead and start. 3,000 just the coefficient. When I take the derivative of a tangent, I'm going to get a secant squared of theta times d theta dt because I'm using a chain rule. And that's equal to, on the other side, dy dt. Alright, plug in all the information we have, and this turns out to be 3,000. Okay, and I have a secant squared of theta times d theta dt, which I'm trying to find. Okay, and that's equal to 880. Now, what I need to know is, what is the secant squared? Well, secant squared at that instant when x is 3,000, y is 4,000. Of course, my z has to be 5,000. Okay, secant is hypotenuse over adjacent, so this will be 3,000 divided by hypotenuse, which is 5,000, divided by adjacent, which is 3,000. That's 5 over 3. That's my secant, and I'll have to square that, times d theta dt is equal to 880. Right. So what I have here is 25 over 9. That's what that is, 25 over 9. So I have a 3,000 times 25 over 9 d theta dt is equal to 880. So my d theta dt turns out to be 880 divided by 3,000 times 25 over 9. Okay, you can leave it like that. You don't have to simplify this. Okay, but this is an angle. This is in terms of radians, so you can write radians, okay, per second. Okay, but the question is, okay, the launch is passed, how fast the camera engine is changing at that instant? Okay, that is, the question is, how fast is the camera elevation angle changing at that instant? Okay, so we're going to say camera angle is changing. Okay, so camera angle is changing. So question. Okay, camera angle is changing at 880 over 3,000 times 25 over 9. Okay, radians per, and this is in terms of seconds. And that's it. Alright, so let's do one more example dealing with cone problems on today's homework, so make sure you know how to do a cone problem. Okay, it says, suppose liquid is being cleared by a segment by allowing to drain through a conical filter. So draw a cone filter, looks like that. Okay, and it is 16 centimeters high. Okay, so the height of this is 16 centimeters. Okay, and then radius of the top is 4 centimeters. So this is 4 centimeters. Okay, and it says suppose that the liquid flows out of the cone at a constant rate. Flows out, that means the volume is changing, dV dt is changing. It's flowing out, that means it's going to be negative. Okay, so at 2 centimeters cubed per minute. So whenever you see cube on units, you know it's volume. Okay, let's just cut to the chase, and then we'll come back and answer question A. Okay, which says, do you think the depth of liquid is will decrease at a constant rate? Give a verbal argument that justifies your conclusion. Okay, in C, when we jump down to C, at what rate is depth of liquid changing? So they want us to find, okay, depth, we'll call that height, dH dt. Okay, when is that changing? When the liquid in the cone is 8 centimeters deep. So when h is equal to 8 centimeters. Alright, so this is a cone. We're dealing with the volume of a cone, so that means we've got to find the volume formula for a volume of a cone. Volume of a cone, well, first of all, volume of a circle is pi r squared. Volume of a cylinder is pi r squared h. And there are 3 cones in a cylinder, so my formula is for a cone is pi r squared h divided by 3. So if I clean this up just a little bit, I'm going to have a pi thirds r squared h. That's the volume of a cone. Now before I take a derivative, I have to ask myself, okay, do I have to manipulate this equation? Because when I take the derivative on the left side, I'm going to get dV dt. I'm okay, I have information for that. And I'm going to get dr dt, which I'm in trouble. And dH dt is what I'm trying to find, so I'm okay with h. So the r is the one that I need to get rid of. And I have to use geometry to get rid of that. So if we really look at this right here, this is the height, and this is the radius, and that's a right triangle. Okay, so if I take a random radius, we'll call that r, and then random height, we'll call that h. They're going to stay proportional because these are similar right triangles, the small one here and the large one. So that means what 4 is to 16 is going to be what r is to h. And of course, if I reduce that, I'm going to get 1/4 is equal to r over h. And I'm solving for r. This implies my r is equal to 1/4 h. I'm going to use that information. I'm going to plug it back into this equation, my volume equation. So pi thirds, I'm going to have 1/4 h quantity squared, okay, h. So if I clean this up, okay, a little bit, I'm going to have volume is equal to pi over 3 times 16 h cubed. I left it as 3 times 16 because you'll see in a second what I'm going to do. Now I can take the derivative of this as is. When I take the derivative of this, on the left side I'm going to get a dV dt. On the right side I have a pi over 3 times 16 times 3h squared dH dt. Of course those 3's are going to reduce. My dV dt now will look like pi over 16 h squared dH dt. Okay, now I'm going to plug in all the information that I have. dv dt is -2, so I'm going to put in -2 for my dv dt. And I have a pi over 16, and my h at that instant, my h is 8 centimeters. So again, 8, and that's going to be squared. And then I have a dh dt. Okay, let's clean this up a little bit more. Okay, so let me create a little bit of a space right there. So I have a -2 is equal to, okay, this is 64, 8 squared is 64, so I'm going to get a 64 pi over 16 is equal to d times dh dt. Okay, so when I multiply by the reciprocal, I'm going to get -32 over 64 pi is equal to dh dt. Okay, and then of course this reduces. Okay, -1 over 2 pi is equal to dh dt. Right. So I'm going to have to write this as a sentence, and I have to write the depth because that's what they're asking. So I say depth is changing at, now when I use the word changing, I can just take the answer that I get as is with the negative sign and write it down. But if I use increasing, decreasing, then I have to be very careful I don't get double negatives. Okay, so we use the word changing at -1 over 2 pi, and this is depth, so that'll be centimeters, not squared or cubed, because it's just the height per. Okay, this is it all in terms of minutes. Okay, so that's my final answer, but I have to go back and answer the other question, and the question is, okay, do you think the depth of liquid will decrease at a constant rate? Well, it's not going to decrease at a constant rate because the volume is coming in at a constant rate. But remember, the cone is getting smaller and smaller, so that means, okay, the height is going to change, you know, at a changing rate. Okay, must decrease at an increasing rate, meaning it's going to decrease faster and faster and faster.